Hi everyone. I just thought I'd do a quick video to explain how I've been tracking the growth of the coronavirus in Italy and now in the United States and in New York State in particular. Let me just start. First of all, this is for educational purposes only. I'm a physicist. I don't really understand epidemiology very well, but I'm able to model data, and so that's what I did. And there's some kind of predictions that can be made out of this. Mostly what I want to ask is how long will this last? Okay. And so let me start off with the theory behind how I did the analysis, and then I'll show you the results that I got. So the first thing we should probably understand is the logistics function. And this function basically is, you can see it there. Let me see if I can make that a little bit bigger. Yeah, there you go. You can see that a little bit better. It's f of x is L over 1 plus e to the minus kx minus x naught. Okay, and what it is it models basically a population growth. Okay, and you'd think that a population growth would continue exponentially forever. For instance, if one person infects two people, and then they infect two more, and then two more, then you'd have 2 to the power n, where n is the number of generations. But the thing is that the population of people is finite. Okay, so the resources are finite, and so this cannot simply grow forever, and it'll eventually max out. So you can see there in the graph that at the low end here, around -4 to -2, I mean, even to -1, it looks quite exponential. But then it goes into a linear phase, and it goes through an inflection point at x equals 0 there. And at the inflection point, the slope is 0, and the second derivative is the slope is positive, and the second derivative is 0. Okay, and then it starts to uh, uh, gain a negative curvature, so the slope decreases over time, and then eventually reaches a maximum. Okay, so why does this actually model population growth? And I guess this was work due to this fella here, Verhulst. I've never heard of him before, but this formula right here kind of shows why it models population growth. If you just had dp by dt, maybe I should tell you, p is actually the population size, and that would be the number of infected people in our cases. Okay, so if you have dp by dt just equal to rp, so without the 1 minus p over k, if you just had that, then you would have exponential growth forever. Okay, integrating that would just give you an exponential. But this 1 minus p divided by k, that represents the resources that are available. And as more people in the population become infected, there are less people to infect, and therefore there are less resources for the virus. Okay, and that goes as 1 minus the population of virus divided by k, which is the population of people. Okay, so p is the population of the virus or infected people, and k is the total number of people. Okay, that's called the carrying capacity. Okay, and of course integrating this gives us the logistic function that we saw earlier. All right, so I'm not going to go into more theory about that. If you want to read up about this a bit more, this is just directly out of the um, Wikipedia page on the logistic function. Okay, now I another piece of the analysis, kind of a minor point, but just for completeness. How did I calculate the first and second derivative, which you'll see that we'll need later? I just used finite differences, and so here, the Wikipedia page on finite differences, I calculated the first derivative using this symmetrical form right here. And well, it's not quite complete, but it's basically x plus a half h minus f of x minus a half h, where h I actually took in this case to be 2 days. Okay, and then of course divided by 2h will give us the first derivative. Okay, so I used the symmetric form of the finite difference there, and for the second derivative, which we will also need, I used this form right here. Okay, that form right there. Okay, so f of x minus 2, f of x minus h, plus f of x minus 2h. Okay, well actually I did x plus h, x, and then x minus h. Okay, so basically just shifted it over one. But okay, that that's for the more math people. math-minded people. All right, now the next thing I need to tell you before I jump into my results is where did I get the data? And the data I obtained using Esri data, and there's two places where you can see it. One is this graph here, and actually, let me move my image down. Let me move myself out of the way here for a second. Okay. Uh, so what you're seeing here is a world map, and basically it allows you to break down the confirmed cases by nations and then by sub-regions within nations. And in the upper corner here, you see the number of deaths and the number recovered. Also down here in the bottom, let me move my image up to the top again. You actually see a graph, okay, versus time, all right? But the data you can either obtain from here or you could obtain it from another place where I'll show you in a second, all right? But let me just show you how you can zero down on a region here. Okay, so basically right now you're seeing the entire world. Currently there's 1.25 million of confirmed cases, of which about 250,000 have recovered, and it looks like 68,000 have died from this, unfortunately. Okay, and so here we have the current U.S. Number, and so you can click on that, and that zeroes in on the US. Okay, and now you can notice in the upper corner here you've got the number of deaths in the United States and the number recovered. But you can further down here, it says admin 0, you can further go down into a more refined, and now you can see here it's broken down by the states, and New York State is up here at the top right there. Okay, and so if you want to break it down even further, you can click on that. And now you could see that within New York State, there is 4,159 deaths and no available data for recovered patients. And you can still break it down further. And now you could see here, you've got New York City, okay, and Nassau, I guess that's Nassau County. And if you want to take a look at Erie County, there's Erie County. And you can see right now for Erie County, we have 945 cases, 26 deaths. Okay, so that's one source of the data. But another source, thank you, John Harris, is this site right here, which is also Esri. And basically it allows you to download a CSV of all the data. And so right here, just click download spreadsheet. I won't do it right now, but it will download the entire data for all different countries. Okay, and so this is where I've been getting my data. All right, now let me switch to my Excel spreadsheet and show you the results. Okay, so put my whoops. My image back up here. Okay, so before I actually show you the results, let me just show you some theory with the logistics curve, so that you have an understanding of why I analyzed the data the way I did. Okay, so here's the logistics curve, and that's a little bit small, so let me try to make that a bit bigger for you. No, that's not how you do it. View, zoom, let's try 150. Okay, I'm going to have to scroll back and forth, but at least you can see the numbers. So the function that I have is actually, let me click on one of the cells and you should see the function. There it is. Okay, so the function is basically that cell C3, and C3 is what I called N naught. Okay, it's just the maximum that it's going to get to. So that's actually the equivalent of K from the Wikipedia page. Okay, and so there's C3, and then it's divided by 1 plus the exponential of C2, and C2 is this parameter which I simply call B, and I set it to 1 for this example here, multiplied by B6, which is the time. Okay, and so there's the logistic function, and what you could see beside it here, there's the logistic function. There is the first derivative, okay, and obtained, as you could see there, as that difference, all right, and beside it I have the second derivative, okay, obtained also as that difference, and over here I have the second derivative divided by n, okay, and I also have the second derivative divided by the first derivative. Okay, and you might wonder why I did that. Well, you'll see in a second. All right, so let's take a look at what this looks like as a graph. So here it is. Okay. Now you'll remember that I set n naught to be 1,000, and you can see that this graph then starts off at 0 and grows up to 1,000. The inflection point, that is the point at which the second derivative goes to 0, or you have the locally perfectly linear slope, is at x equals 0, or sorry, t equals 0, because we're talking time here. Okay, and so it grows up to 1,000. Now if I were to change some of those parameters, let me just show you very quickly here. If I were to change this to 2,000 like that, then scroll back over here to the graph, and you can see now that it now increases up to 2,000. Okay, so let's just leave it at that, and at 2,000, and let's take a look at what the first derivative looks like as a function of time. So there's the first derivative as a function of time, and you'll notice that it grows, and it grows up to 500 and then drops off. Okay, and that 500 actually scales as the 2,000. So if I were to change that 2,000 back to 1,000, like so, okay, you'll see that again the logistics function maxes out at 1,000, and the first derivative now maxes out at, has a peak of 250. Okay, so you could see that the n is a function of time. That's the logistic function as a function of time. Its first derivative and even its second derivative will scale as n. Okay, so as n increases, the peak of those functions increase. Let's take a look at what the second derivative looks like. Here's the second derivative as a function of time. Okay, and so you could see here that before t equals 0, before the inflection point, the slope is positive. Okay, and it actually increases, but then it starts to decrease and actually goes to 0. All right, so at that point the curvature is going from positive to negative. In other words, the slope was increasing, and then it stops increasing, and after that point the slope starts decreasing, and then eventually the slope goes to 0 when the logistic functions bottoms out. Now the reason I'm bringing this up is because we really want to find that inflection point, because that inflection point will tell us ahead of time. If we can predict where that inflection point will be, that'll tell us how long the pandemic will last. Well, I don't know about the pandemic. I should say locally at least. It'll tell us how long this will last, and that's the main purpose for why I'm doing this. I mean, other things like how many people will die and how many will recover and things like that might be extrapolated too, but my main purpose for doing this is just wondering how long do I have to sit indoors. Okay, so you could see that the inflection point is midway. Okay, and so when you see that inflection point, you know that how long it took you to get to that inflection point. Well, double that, and that'll tell you how long until finally the locally the disease will end. Okay, of course there could be reinfections and so on and so forth. Okay, and I guess one other thing I should say, well, I'll say it when I get to looking at the data. Okay, and then the other thing is the problem here, that this maximum here, or the size of these functions, actually scales as n naught. And so what I did was I also took a look at what would happen if you took the second derivative and divided it by n. Okay, and that might be a little bit too big to fit in there. Let me just decrease the zoom just a little bit here. All right, let's see. Yeah, you can see that. Okay, so here I've got the second derivative divided by n, and you can see that the second derivative drops, and it still goes through 0, okay, at the inflection point, but it's got this kind of a funny shape to it. Okay, but nonetheless, what this does is you'll notice that that's 1 there. Okay, and so this doesn't scale as n, because n, the second derivative scales as n naught, the n itself scales as n naught, and so if you divide it 2, then the n naught will divide out. And I don't know n naught beforehand, so this is just one way to getting rid of n naught. It gives a kind of a funny shape to the curve, but at least you could see that when it reaches 0, that you've hit that inflection point, and that's the essential point here. Another way to do that, I looked at a second way to do that, and that is to just take the second derivative and divide it by the first derivative, and this gives a more symmetric curve. And once again, because the second derivative goes to zero at the inflection point, then the n double prime divided by n also goes to zero. Second derivative divided by the first derivative will also go to zero. Okay, so I'm looking for that inflection point, and once again you can see that that's one there. Okay, because what it's not going to scale. It's not going to scale as um, and not. Okay, it actually scales as b, but that's okay because b is just some finite number. It isn't like some large number. And just to get rid of some of the large fluctuations in the graph. So okay, so let's take a look at some of the data that I looked at. I looked at two things. I looked at confirmed numbers for Italy and also deaths for Italy. So here's where I should say something about the data. You might wonder why I didn't look at China, and there's rumors that China, because it's a communist country, might be lying about its numbers and so on. But I have no direct evidence of that. But what I do have evidence of is that they changed their criteria for what defines a confirmed case. And as a result, it makes it very difficult to plot that on a graph, because what you have is basically, like one definition for n, and then you've got a different definition for n. And what does that look like? Well, you can actually see it, and I think it's around mid-February. I can't remember exactly the date. There's this huge spike of about 15,000 cases, which just sticks out. And you can see that it looks like a logistics curve up to that point, and then there's this huge vertical jump, and then it continues on that logistics curve, and you're wondering what do you do with that? Do you factor it out or something like that? Whereas at least with Italy, I'm assuming they were fairly consistent in the way they did their numbers, and other countries are consistent in the way they do their numbers. Now, they may not be the same, and so I'm not sure, but like Germany might be doing them differently than Italy might. But as long as they're consistent, at least I'm getting the shape of the curve right. If not, maybe truly the number of people that are infected. Okay, so if you're consistently getting, say, 10% of all the if the confirmed cases is like 10% of all the people who are carrying the virus consistently, then at least you're following the same curve, even if it's off by a factor of 10 in that case. Okay, so that was the logic there. And I looked at confirmed cases, and I also looked at deaths, because deaths are a little bit less questionable, whether or not they are due to the coronavirus or not. Though even there is some question, because if someone dies because of underlying conditions that were exacerbated by the coronavirus, you can say that that the coronavirus caused that or not. Okay, and apparently there's some dispute about how Germany does that counting versus how Italy does it, and so that might be one of the reasons why there's a discrepancy there. Again, this study is really not meant to um, look at these total numbers because they're part of the definition. As long as the definitions remain consistent, I'm really worried about how long I have to stay in the house or how long this will last in my local region. Okay, so having said that about the numbers, here's the numbers for Italy. Okay, and maybe I should just show you a little bit of what I took to be day 0 or day 1. Okay, so okay, I got to make that bigger again. Let me just zoom in again there. Okay, and so what I have here is I took March 1st to be day 1 for Italy, at which point there were 1,128 confirmed cases. All right, and you could see that across that column there, I have I did some other tests too, like I looked at the log of n and percent increases per day, but really the numbers that I kind of zeroed in on for answering my question were the second derivative divided by n and the second derivative divided by the first derivative. Okay, now there was actually a lot of noise even at that point, so what I decided to do was to average them over 7 days. Okay, so I went back 3 days, so the day itself, and then back 3 days, and then forward 3 days. Okay, the incubation for this I've heard is 14 days. I'm not sure, but 7 days seemed to smooth out the data enough that it looked like something that you could look at and go, oh yeah, I can make a prediction from this. Okay, so I tried 3 days, and there was a little bit more noise, but it didn't change my prediction that much. So well, there it is. Okay, so let's take a look at the graphs. Okay, And here is the graph for number of cases. Let me just shrink that down a bit. I want you to be able to see the, the title there. Okay. So there's the number of confirmed cases versus time. Okay, and you can see that it's going up on what looks like initially here an exponential. And then is this linear? Is it starting to curve back? Yeah, I don't know. I don't know. But it doesn't look like it's continuing just purely exponential. It does look like it's starting to flatten out there. But let's not try trust our eyes. Let's see what uh, the second derivative says. Okay, so if you look here at the second derivative, now this is the second derivative divided by n. You could see that it's up here and it's kind of bobbing back and forth. I still don't like that's too small. Let me zoom in again. Okay, so sorry, you won't be able to see the title, but let me just show you what the title is right now. It's the second derivative, that's n double dash divided by n, averaged over 7 days versus time. Okay, and time is measured in days. All right, so over here, you could see the graph. Lots of noise. All right, but it looks like it's got this downward slope here, and it hits zero somewhere around day 25. Definitely, it's been at zero for a while now. Okay, so even if you were to say that, maybe 30 days until the inflection point, that would mean it's 1 month in till you get to linear behavior, and then another month after that until you've basically hit the saturation point of the logistics curve. Okay, and this is making a lot of assumptions. Like I'm not making any assumptions about the underlying dynamics. Like you're saturating a resource, but does this mean the entire population? Does this mean, or does this just mean the available population? Because a lot of people are self-quarantining. So if someone like perfectly self-quarantines during this entire period, well, they're not part of the N naught that I call the population that could be infected. Okay, so there's a lot of assumptions here. Like maybe they'll come out of quarantine and then it'll start up again, and then that would be terrible because then we'd have to self-quarantine once again. But you could see here that roughly 30 days. Okay, and let's take a look at also the uh, second derivative divided by the first derivative. Again, it doesn't give much different data. It's just a slightly different curve to it. And I'm going to see what I want to follow both of them as this progresses all the way until the logistics curve actually saturates. Okay, and here's what that looks like. Okay, and you can actually see that indeed it's gone negative. Okay, between a lot of noise in here, but between day 25 and day 30, it's definitely crossed the zero there. Okay, so on this basis, it looks like Italy is at the halfway point, and they have another 30 days until they're pretty much out of this. Okay, and if they continue the self quarantine for 2 weeks after that, and the incubation is 2 weeks, well then it's eradicated. Uh, uh, could it resurge? Could they be reinfected because people will start to come in? Their borders are closed, but at some point they're going to have to open them up. I don't know. I mean, like, I just want a rough idea of like how long this thing is going to last. Okay, so there's the story with the Italian, but confirmed. Same sort of procedure with deaths. Okay, and so here you could see that I have day one is again March 1st. Okay, and I have the number of deaths. All right, got the number of deaths here. And then I've got the second derivative divided by the number of deaths, and then averaged. And then also the second derivative divided by the first derivative, and again averaged. Okay, so let's take a look at what those graphs look like. So here is deaths versus time. All right. And again, looks characteristically exponential, but then is it going linear? It looks like it. Maybe it's even curving down there. I don't know. I mean, uh, maybe like that's why we'll look at the second derivative here, and here's the second derivative divided by by, well, this time I called it d for deaths, okay? So second derivative divided by d, and you can see that it's going down, and it looks like it's hit 0 at the 30-day mark, okay? So at 30 days, uh, they've reached the inflection in the deaths. Now, this is not population growth, okay, but it's I'm gonna assume that there's some kind of relationship between the number of people that are infected and the number of deaths, and that is a constant fraction, okay? So like I've heard all sorts of numbers, but like, let's say it's 1%, okay? It looks like the 3% was a little bit high, but I don't know, not my expertise. So let's say it's 1%, okay? So basically, the deaths are basically following the number of infections, and it might be a more reliable number simply because a death due to coronavirus might be something that you're more certain of than a confirmed case. Okay. And let's take a look now at the second derivative divided by the first derivative. Same story, okay? Once again, it's just a slightly different way of presenting the same data. And you can see there it's crossing into the negative at the 30-day mark, meaning that we're halfway through that logistics curve. Okay, we're at the inflection point for Italy. All right, now great, this is the Italian numbers. Let's take a look at the US. This is the entire US because I live in the US. Okay, and let me switch down to, sorry, I keep switching the sizes here, but it's kind of hard to see otherwise. Okay, so here's the number of confirmed. N is the number of confirmed cases, and you can see that it's growing, and that looks exponential to me. Okay, I'm not totally sure. It looks exponential, and if you take a look at the number of deaths, they're like that, and that also looks exponential to me. Okay. All right. So are we anywhere near the inflection point for the United States? All right. Well, um, let's take a look here at the second derivative divided by n, and lots of noise here, and but if you can take a look, it's sloping down as you expect, okay, but it's not near 0 yet, okay, and I don't know what this is going to do. It's probably going to bounce a bit. Is it are we looking at maybe 35 days, 40 days? I don't know, okay. um, um, Not totally off from where Italy is, okay, and the predictions from Italy being that it's 30 days to inflection and then another 30 days until saturation. Okay, so it looks like we're not totally out of that ballpark, okay, but we're not at the inflection point yet for the United States, okay, and similarly, so we're lagging behind Italy. All right, and similarly, if we look at the number of deaths, second derivative of the number of deaths divided by d, okay, yeah, we're not at 0 yet, okay, so we're not at that inflection point yet. A slight downward slope, okay, well, not slight, but noticeable downward slope. But where's this going to extend to? Well, there's 32, maybe 34, 35. Okay, day 35, we might be there. All right. So let's take a look at the other way of presenting this, which is the second derivative divided by the first derivative. And you don't expect this to give you anything different. It's just a different way of visualizing the same data. This one actually looks a little cleaner. Okay, so again, we're not near that inflection point, and a lot of noise with the number of deaths. Okay, so, but yeah, no, we're not at 0 yet. We're not at 0 yet. In fact, I don't even know if I could say that there's a downward slope to this at all. All right. Okay, so let's zero in a little bit more to home. Here's New York State data, and for New York State data, there is the number of confirmed cases versus time. All right, and some noise down here, but is this exponential? Yeah, it's definitely got a curvature to it. Okay, and if you take a look at the number of deaths versus time, that one looks definitely exponential to me. Okay, and I can't claim that it's going linear there. Okay, so let's take a look at the second derivatives. All right. And so I probably should have removed some of this noise up here because this is kind of like squishing my scale. But you can see here that this is a downward slope, but it's not at 0 yet. Okay, so this is second derivative divided by n. All right, second derivative of confirmed cases. Over here, there it is for deaths. Okay, and again, that has not crossed the 0. All right, and then the other way of visualizing it is as the second derivative divided by the first derivative. And you could see here, here's confirmed cases, and over here is deaths. Okay, and again, neither of them are crossing the 0 at all. So no, we're not at the inflection point in New York State. So we've still got a ways to go. All right. Looking at this, I don't know. I mean, should I make a guess here? Uh, Look here, it's 7. Here's 12. I don't know, maybe out here, what would that be? That would be maybe another week, uh, something like that. So maybe in another week we'll be at the inflection point for New York State. All right. So what does that mean? Probably like 40 days until this is over for New York State. Well, let's go even closer to home, which is Erie County. And unfortunately, with Erie County, I just don't have the numbers because they're kind of small. But I mean, I'm starting to track it, and I'll report when I get more data. Here is the number of confirmed cases versus time. This doesn't look like it has any pattern, maybe linear at best. Okay, and here are the deaths versus time. Okay, so yeah, you can't really say much from this. All right, like we've only got like under 20 right now, or at least as of when I did this graph. Okay, or I think we're over 20 right now. Okay, and if you take a look at well, I didn't even do the other graphs. I didn't even do the other graphs because they would just be noise at this point. Okay, so anyhow, what's the conclusion here? Well, from the beginning of when this starts in your area until you hit the inflection point, that would be 30 days if you followed Italy. And then from the inflection point, which is the worst moment for that area, until finally you hit the saturation, that's going to be another 30 days for a total of 60 days until you're basically out of it. Well, I mean, I don't know about any repercussions after that, but there it is. Okay, so this was my analysis.